So we have found out the correlation, and as such we have not seen any correlation, right? So as I told you, if it's 1, then we can say it's highly correlated. It's 0.999, then we can say, but over here we can see the values are very less, either if they are negative also. So that means no column is highly correlated with each other. That is, no such two columns are there that we can represent the same value. So every column over here we can say it's important. So we can't drop that. So that's why also we are finding the correlation value. So now what we want to see, we want to represent the target variable, that is the whether they're having disease or no disease. So we'll see what is the percentage they are having, that how many data which we are having over there. So let's quickly do that. We'll represent the target variable in the percentage. And first we'll count no disease. Find out the length and from the data frame. We'll define it. You have to tell the heart disease. And the value which should be equal to 0, that you need to tell. And the same case we have to find it for the 1. We'll see how many cases, so that we can see whether we are having imbalanced data or not. So now we'll print the value. And we'll see percentage of patients have not heart disease. All right. And that will take, because it will be the value. Will not use the format. And all right, let's take. We'll just count no disease, that which we have just taken the variable. And we'll divide it by length of the total. And then we'll multiply it by enter. We'll copy this one quickly and then paste this one. And over here have heart disease. We'll see that. Count no disease instead. We'll write. Over here I have to change have disease. We'll write over here also have disease. And that will be the same because that's the total. Yes. Let's print it. Okay, there is one error. Okay, heart disease. It's in the line. First one. We have, okay, over here it's heart. That's the typing mistake. Yes, done. And it's not showing the value. That we'll have to see why it's not showing the value. Yes, count no disease is like, yes, yes, it's heart disease. And yes, it's nothing. Let's, it is not finding the format. Okay, we'll just quickly print it out then. We'll just count how many. We'll just target it. We'll see in this heart disease. And we'll just give the value count. This is a function which is already there for value counts. And execute it. Now, so now over here we can see this. We are having one value, that is they are suffering from the heart disease. It's the 165, and if they are not suffering from it, so that's we are having 138. So that's the value which we are having. So over here we have found how many of each class. So for the one we are having 165, and over here we are having this, we can see it's 138, right? And if we'll go with the percentage, because we have calculated the percentage, the count no disease, so it would be like which have not heart disease, it would be like 45%, and which we are having heart disease is like 54%. So the data is quantitatively balanced, so that is the balanced data, so we don't need to worry about that. And if we want to see the graph also, whether they are having the balanced and imbalanced, so we can just quickly draw the graph, so that will represent more better understanding for us. We'll just write again heart disease. Right, and over here there we are going to use again value counts, the function which I told you. And then we'll plot the graph. So we have plot the graph. We're going and we'll plot kind. What it's kind, I want to show the bar graph. So we'll say it's a bar graph. And let's take the color. We'll change the color also. And let's take for, because it's two classes, so we'll take salmon and the light blue color. All right, so this is for the color. And the next parameter which we can give is the title of the graph. So let me give the title. And I want to give that it's a count of diagnosis of heart disease. All right, and just execute it. Done. So now you can see the graph also. So now over here we can see this graph shows that the count of the populations is having disease, right, and not having disease, as we have seen over here. And the one value we can see, the who are having disease is slightly greater than who are not having the diseases. So now we'll again plot, because one thing you can do in EDA is that even you can, for every column, so which you're having, so you can see with the gender also, that in which we can say the how many males are suffering from the diseases, or how many males are suffering from the diseases, heart diseases. So from that we can predict, okay, the heart patients are morely like to be happen in the female gender, or we can say in the male gender. So that we can also do with that. So let me see if how many we are having in the female gender and in the male gender. So for that we can just write the column name. That's we have written gender. Okay, there is one question. I'll check.
So far it's clear, ma'am.
Okay.
So code once, ma'am.
Sure, sir. I'll share that. Okay, let me do. Yes, so we have taken gender and over there we'll count the value. So what we are doing into this. So we have to see for every column whether it is having any impact on checking whether the person is having the the heart disease is suffering from or not. So see over here for the gender which we are talking about the male. So in the 303 total cases we are seeing for the male it's 207 who are saying we can say it's 207 and for the female we are having 96. So we are having the data, it's like this. Heart disease, if we'll say, and if we'll just write the compare the target column also with the heart disease because we have just checked with the gender how many male and how many female we are having. So over here, let me just check with the heart disease also. So now if we'll see as compared to the heart disease. So 0 means they are female on the gender. So if the female 24 and they are not suffering, 0 means they are not suffering from the heart disease. And one that is are suffering from the heart disease. So out of total 96, we can say 24 are not having are not the heart patients and 72 are suffering from the heart disease. And out of 207, we are seeing that 93 are the one who are suffering from the heart disease. So this we can got it from here, that is from the cross step function, and even we can plot the graph also for checking whether what is the ratio of the population having the disease and not having to disease with respect to the gender. So I have shown you the data and also you can just draw the graph also if you want to draw. If you want, just let me know, I'll draw the graph, but and in the same way you have to find the relation between the maximum heart rate and the chest pain type with respect to the gender. So if you'll do with accordingly to every column, then only you can interpret, okay, the gender male have high median if we'll say, and if compared we are female, then we can say that which column is signifying what, that which is the typical angina is having higher with respect to the maximum heart rate in both the gender. So that thing you can do with the help of the graph only. So that is the beauty of the graph. If you'll do the visualization, that we can do with that. And you can see the other graph also. I'll show you the code of these things. Yes. So see, we have just done the count. So this we have already seen what is the count. And over here we are just doing the heart disease, that with respect to the gender, that also we have seen, and how many gender in how many cases we are having for the male and for the female. So same thing we have just drawn for the graph also. So over here you can see it's the amount how many cases we are having, and over here this is for 0 and the 1 no disease, and for the over here you can see they are having the diseases, and it's for the orange one is for the male and the blue one is for the female. So from the graph we can just see the ratio of population which is having the disease and not having to disease with respect to the gender. So that's what we have done, and same case we have built for the other columns also, that is the maximum heart rate versus the chest pain. So that we have seen with respect to the gender. So over here we are building the Violin plot, and you will see we are taking the values first maximum heart rate and this gender one, and we are taking that value and taking data from the data frame. And for the x value, for the x-axis we have taken gender, for the y-axis we are taking the heart rate. So this is the gender 0 and the 1, that is for the female and that is for the male. for the male. And over here you can see the maximum heart rate. So as you can see the Violin plot, so we have built the Violin plot, and you can see for the gender male we are having the higher median, and you can see this region if we compare to the female and the chest pain type 1, as you will see. So this we can just predict that it is a atypical angina, and which is higher, so with respect to the maximum heart rate, right? So from this we can see in the male we are having the maximum heart rate. Okay, and this we have just built, and the same case we can do with the second one, that is the second column, thalassemia types, and we can see the ECG result and with respect to the gender also. So row we are taking it, and columns we are taking is thalassemia type, and now we are taking it as ECG results. And over here you can see the result also. I'll show you the result, as now we are building a different plots, because we are having a different categories of thalassemia, that is 0, 1, 2, 3. And we have seen the different categories of thalassemia as 0, 1, 2, 3, which we have which we have already discussed in the further, that if the thalassemia is 0, then it's what type, and it's 1, it's of the which type, right? So that's what we have done, and it's for, you can see it's for the female if the gender equal to 0, and if gender equal to 1, it is for the male one, right? And that is the relation between the resting electrocardiogram rate and the thalassemia with respect to the gender. So we can just see over here. So there is a very slow difference. You can see there is nothing over here. That is just line. And now for the type 2, it increases. So for the female thalassemia rate, we can just see, and it's the type 2. And for the type 3, we can just see thalassemia is over here for the type 3, right? So that displays the maximum heart rate over here, right, by the individual. And if you'll see in the male part also, that's also the over here, there is some slightly ECG result will show. And for over here, we can see there is slightly less as compared to the female, but there is a high rise in the type 4 if we compare with the female part, right? So over here, we can just predict that this histogram which we have plotted between the electrocardiogram and the hemoglobin, this will lower the effect with respect to the gender. And it will show, because we have seen in both the gender, they have same rate, the rest ECG, but the hemoglobin defect type 2, right, is greater in males, this one, whereas the hemoglobin lowers reverse effect type 3 is greater in males, and they are lesser in females. So we can just analyze this, that what is greater in males and in females. So therefore it is tough for female to get back the hemoglobin content. So if there is a loss, on the other hand, it is easier for men to get back the hemoglobin content. So this is the inference which we get it from there, from the analysis, that which should the hemoglobin would be higher for the male one or for the female one. So now if we look for the another property, that is with the age part. So now this is the histogram of the age which we have built. So now if we'll see the histogram between the 30, and because we have seen the lowest age is the 29 that we have seen. So it started from here, that's why. And the mostly the ages lie between 40 and to the 65 or 67. So mostly age is like that. And now over here you can see also. So mostly when the heart disease or the heart patient can become the likely the age. So you can see the older, we can see it's between highest peak in between the 55 till the 65. So that patient, then we are having the age of 65 to 55 to 65 that are most likely to have the heart diseases. So that's we have checked from the histogram, and now we have seen the how many different types of categories are there for the maximum heart rate. So we'll just scroll down, and now we can see these are the categories. This we have just built with the help of the graph also. And this is the coding which we have built. So you can see over here that the target when we are having is equal to 1. So we are just building the scatter plot and heart disease with respect to the age, and we are getting it over here with the maximum heart rate, right? So that's what we are doing it over here. Maximum heart rate and the age, that's we are building. So again, for the 0 with respect to the age, so that's the graph between the two axes we are building. And then with the age, we are just finding the maximum heart rate, as you can see, which is equal to 1 and which is equal to 0. That's we are going to do. And the title we have given, heart disease in function of age and the maximum heart rate. And x label we have given age, and y axis maximum heart rate, and that will represent disease and no disease. So over here the blue lines, so blue plots which you have seen, it's like no disease. And you can see the maximum heart rate, what is the heart rate when they are the maximum, and when they have reached the maximum heart rate, as you can see, this blue one is the maximum one, right? And over here we can say that yes, it's a disease one, because the maximum heart rate is higher at this point. And you can see the higher points also, these are the diseases one, and the orange one, it's higher, but over here they are not diseases, right? They are still not suffering from the diseases, but get the chances. And over here you can see heart rate is normal, that is the down one. And even for the blue one, then also they are suffering from the heart disease. So it's not like that. So we have to count that how many plots or how many cases we are having from this, right? So this shows the maximum heart rate of population with and without diseases, and with respect to age also. So you can see the age at which they are suffering from it, right? So that's what. So for every column we have done this, and over here you can see the relation of heart disease with the chest pain type also. So if the person is having the chest pain, right, 0 is not having a chest pain, and 1, so these are the categories which we are having in the chest pain. So we are having the rows. So we have already discussed the categories of the chest pain which we are having, right? And then because chest pain time is the 0, that typical angina, 1 is the atypical angina, 2 is the known anginal pain, and 3 is the asymptotic. So as you can see, and 0 is not disease, so they are not having any disease. And for 1, so these are having diseases. And maximum is the type 2, that is the known anginal pain. So now you can see heart disease with the chest pain type, right? And if you want to see the graph or the visualization, we have done the graph also. So this is the graph which you can see. For the same, we have done the same with the data and with the graph also, so that it's very easy to represent. So that frequency, the graph which we have just shown, it shows the frequency of each chest pain type, the categories which we are having, 0, 1, 2, 3 for the population having and not having disease, where type 0 is greater, where the population is more prone to not have disease, right? So as we have seen in over there. So this one, population 0, because it's not having the disease, right? And if we'll talk about the next column, that is the resting blood pressure. So we have drawn the graph also, and this graph which you have seen, it shows the density of the resting blood pressure, and the maximum is around 120 to 140. So which we have seen that it should be the normal one. So that is like that. And the next one is the chesting pain versus the resting blood pressure. And over here we have seen what is the chesting pain from this diagram, from with respect to the gender. And over here chesting pain for the 0, and for 1 we are seeing orange one for the male. So pain is more severe in females if we'll talk about, and there is in this value will lie for the male part. So as you can see, there is a more value because we are having more data of the male. That's why the value is like this. And for this, we can say that the males, because we are having more of males, orange lines, that are more prone to the heart attack with comparatively higher level of the blood pressure, because they're having higher level of blood pressure than the females. So that we got the inference from the graph that males are more prone to heart attack with comparatively higher level of blood pressure than female. So that we can see in the heart diseases versus the fasting blood pressure. So if we'll see in that also, so you can see heart diseases 0, that is heart diseases, and fasting blood pressure. So over here 142 cases, they are not having fasting blood pressure, but they are suffering, right? And that's we have plotted also with the help of the graph. And over here we can just say that sugar level, because does not contribute to having or not having the diseases, right? Because over here we can see the 0 not sugar level, and over here we can just see how many values we are having. And for 1 they are having blood pressure and only 23. So blood sugar and having heart disease, it lies between a very small value, and as you can see over the graph also. So that's why we are saying this sugar level does not contribute to having or not having, so we can't justify that. And the same case we have done with the cholesterol, as you can see. And this we can say the higher having the cholesterol, right? A cholesterol level, and the heart rate will be the less. So as we can already know, the cholesterol brings the higher heart patients, and this occurs mainly in the men, as you can see the median over here, and it occurs mainly in the case of the men, right? And now we have seen the ECG results also. So if you see the ECG result, so this is the category. For the 2 category, it is 1 only, and for the 1 category, 96 patients. For the 0 category, it is the 68 patients. So for the heart disease, so for the true value, so it is making an impact for the category 1, right? So now as you can see in the graph also for the ECG. So this shows the frequency of each ECG type for the population having or not having disease. It is greater in the type 1, and these are more prone to having disease. So see how we have performed the CDA, and with the help of each column we are just finding out which is having the more effect and which is not having the more effect. So you can see in the type 2 also thalassemia, as we can see in the graph, right? So this graph shows thalassemia type for the population having and not having disease, where the type 2 is greater, and this type 2 is more prone to have the heart diseases. So that's what we have done. And now what we need to do, so that is the cases, that is the EDA part which we have done, and I'll send you the code also, so you can just try and read the code which I have just explained. And these are basically the graphs. So if for visualization, even for understanding the data analysis and what we have done, so the better part is that you should draw the graph and understand from there, so it would be very clear from the data and instead the from the graph instead of the data. So that's what we have done. And now what we need to do, we have to perform the modeling. So for the modeling, what we need to do, we have to experiment with the model. So we will apply, we'll do with the logistic regression, because we have studied logistic regression in the morning, right? And with the help of the logistic regression, we can just we'll apply, and when we'll study the SVM, then we can apply over the SVM also. So we'll see what is the accuracy and what are the parameters which we are going to take over there. So now let's come again to this part, right? And let's build the model. So now we'll build the model. So for building the model, so because we have to take the first we'll see the head value, what columns we are having. So over here you can see these are the columns and these are the values we are having. Okay. So now what we need to do, we have to split the data. So now, because as you already know, the data set which we are having, first you need to give it for the training part and second for the testing part. So you need to split that data. So why we need to split the data? Because we don't want that the same data is used for the training and for the testing parts. Like when we are having the data, we are having 303 rows, and from this we have just divided the data into 2 parts, and 30 rows we have just get it out and saved it for the testing part, so that for the training we'll just train the data from the training part. And for the testing time, so when it get the new data, because the data it has not received any prior information. It has not seen the data before the values, but we have trained the data according to the basis which we are going to use. So when the new values come, then only we can predict how our model is working, whether it's working good or whether it's not working good. So that's why we have to split the data into two parts, training and the test splitting part. So for this, first what we need to do, we need to tell what is the value of x and what is the value of y. So I told you in the morning lecture, we have to take the equation like y is equal to mx plus c, right? And over there, that you need to take, and we are having more than one value of the x. So if you are having more than one value of the input or the features, then equation becomes a different one, that we are having a different value. So b0 plus b1x plus b2x plus b3x, so on to bn. So that's the same case we have to take. So the x input we are going to take for the x value, we are going to take for the input, and into this I want every data, every column, as we have seen over here. Just besides, I just don't want to take this heart disease one, because this is the output one. So I don't want this one, else I want rest all the columns. Okay. So for the x parameter, that is for the input which we are going to take, we'll just drop this column heart disease, because this is our output which we want to predict, that is value of the y. So heart disease, and over here x is equal to 1, that means the column you have to take. Okay, so let me run it. Done. And now the value of y. So for the y from the data frame, I only need this heart disease. I don't want any other. Okay, so that's the thing which we need to do. Y is only this column heart disease. Done. And now here comes the part that we have to train and we have to split it, because now you are having the x, that is the features and input, and y we are calling it as a output or the target that we have to predict. All right. So now the data x also you have to divide it into two parts, training and the testing, and y also you have to divide it into two parts, training and the testing. So let's do that. X train and then X test, and then we can take Y train, and then we can take Y test. Okay, and then because we have uploaded one function, and how this splitting will be done, so for that we have imported one function, and let me just scroll down, and this is the function. From sklearn model selection, we are importing this train test split function so that we can just divide it. Scroll down, and then we'll use this function train test split. And now the parameters. So the parameters which we have to pass it over here, that we have to see. So the first thing which we need to do, is that we have to pass the value x, and that is this value, the features. So that's why they'll change it into training and the testing parts. And for the y, we have to pass this output variable, the target one. And then we have to tell also that how many size you want it for the training part and for the testing parts. So you are having 303, that is 100% data. So for that, I want just 20% of data would be given to my test size, and 80% data ultimately will go to my training part. So, and the data should be taken randomly. It should not be taken by serial order. So that is the random state you have to take, that you have to do randomly, you have to perform. Okay, so now we have, let me just execute it. Yes, done. So now we have executed, so we have to train it on the training set, and we have to find the patterns, and then we have to test it, and we'll use that pattern on the test set also. All right. So for this, even I'll show you the X-train shape also and the data also. So you can see from the 303 rows, 242 goes to the X training part, and the 13 columns. Total were 14 columns, but now we are having only 13 columns because the last column we have given to the output, that is the Y. And if you want to see the X test also, so see 61. So this we have given test, as you can count it, that is a 20%, and 13 columns for the X test. And we'll see the data also, X train and the X test. So see, these are the data. So see the column, the index value are the random, right? These are the index value. And let me come to the X test. Now you can see the values which we are having over here is not present, it's the X train part. So that's how we want to get it. So the same case with the Y train. We'll see its shape first. Oh, it's a small Y. So now you can see 242. And if you go for the test, so now you can see 61. All right. And if you want to see the data, so these are the data. 0 not disease and 1 is the disease. So that's how we got it. So now we have split also. We have done the splitting. So the next part is that we have to apply the logistic regression. Okay. So for applying the logistic regression, so the model which we have to build, we have already done that. Let me show you the code of importing it logistic regression. Yes. So see line number 13, which we have executed. Yes, so over here we have imported this logistic regression from the sklearn library, where we are going to use this logistic regression. So let's do that. It's a classification because we are doing 0 and the 1, right? Output. That's now we'll take one variable LR, and into this we are calling the function which we have just imported, that is the logistic regression. Logistic regression, and that function we are storing it in the LR variable, because I don't want to write every time this full function, so I'll just assign it to a variable, right? And then we are having the fit function. So fit function we are using for training our model. So now it's time to train our model. So now with the help of the logistic function we are training the model. So now we have to just write xtrain, and because you are providing the training on the basis of the xtrain and ytrain. X is the features and Y is the output. So that's how we have given it, that you have to fit is the function which is used to provide the training. So let's just execute it. Done. So you can see this is done already, and you can see the logistic regression over here. And if you want to see how much score we are getting, so score is the already parameter which we are having. And if you want to see the training, how much training they have given, so you can see the score. So that would be obviously 1. That is 100%. Now you can see the score that at the time of the training it will take randomly, and the score it comes out to the 85%. That at the time of the training they have scored like this 85%, right? And there is one more thing, that is with the case of the probability. So if you want to check what is the probability of getting the value, so that is the function, that is the name of the variable I am giving is y underscore logic underscore probability. And then we are going to predict the probability. Probability we are going to predict on the basis of LR, that is logistic function, and predict underscore, that is the proba. Proba is the probability which we have to get, and we are getting the probability on the basis of the X test, because this is a question paper which I have to give, and the test one, so which they will predict, that is the Y logic. So let me run it, and you can see the value of Y logic probability. These are the probabilities which you are getting with the help of this function only, right? And on the basis of the X test which we have given. Now we'll just predict the test variable, that is actually the value which I want to predict. Let me change it into that, predicts. And then we are going to predict. And then over here, we are going to pass the value. That is again the X test, because on the basis of the question paper, you can check whether what would be the value for that. So let me print its value also and run it. So now you can see it's 0, 1. So over here threshold value is applied, and now you can see that's the probability. And over here you can see the value it's changed between 0 and the 1. That's in the case we want require whether this person is suffering from heart disease or not, right? So now we'll see the score in the testing, how they have done in the test, and with the how we can compare it, because the answer sheet is the X test which they have done. Right now just the X test we have passed and the Y test we have passed for them. So for that, we have to see the testing accuracy also. So let me just print. So let me run it. Okay, there should be comma. Yes. So it's 88%. So now testing we can see it's a good one. So for this, we have to draw a confusion matrix, and we have to generate the confusion matrix, because we want to see how my classification report is doing and everything. So there is one more thing I'll for the parameters if you want to see. So let me print the classification report also. So there is one function that is with the classification report, and we have uploaded it, we have imported it earlier. I'll show you. Yes. So now you can see classification report and the confusion matrix. All right. So let me go that. Yes. Now this is the, again, you can just write because we have imported the function. And over here, we'll just pass the Y test, because that's the answer sheet which we are having. and we have to compare it with the value which is passed, which they have given, which the students or our machine has given, that is with the name of this. This is the predicted values and the original values at y-test. So we have to compare it, and on the basis of that, we have to give the classification reports. So now let's just run it. And now when you provide the classification report also, so over here we can see, right, it's for the 0 and for the 1, precision value, recall value, and the F1 score value. So just tell me this one, are you familiar with the precision? And over here you can see the accuracy, that is 89%, which we are getting over there. So tell me, what is the precision, recall, and the just precision and recall? What you understand by precision and recall? These are the parameters which we are taking from the classification report. Okay, let me go into this. Okay, there is. Okay, I'll show the code once. I'll show the code, don't worry. And I'll share it also. Yes, that's what I'm explaining, the performance measure, precision, recall, and everything. I was just asking. If you want to identify, ma'am, which is the feature, so first thing you have to understand the correlation. So you have to find out whether there is a correlation between the different features and the different features which you are having. So which feature is impacting the more of the output which we want to predict. So that we have done on the basis of the graph we have built and the values which we are getting. So on the basis of that, you can identify and you can drop any feature also if it is not impacting. So in that case, in this case also, there is one feature which is not impacting it, but we have not dropped it. But we have used every feature. So that's the thing which you can do. So first you can apply with all the features, and the analysis which we have done, that there are 1 or 2 features which are not important. Then what you need to do, you need to drop it, and then again you have to apply the model, right? Okay, yes, I was asking. I'll show the code again. I'll show you the code. Don't worry about that, and I'll explain it again. We'll just do the quick recap of the code also. So just tell me precision and recall. And before that, it's good if we'll draw the confusion matrix, right? Because confusion matrix would be the good parameters to show that. So for that confusion matrix, we can just use the heat map and we can just draw it. I'll just draw the confusion matrix first, then we can talk about it. All right. And first we'll draw the confusion matrix, then I'll explain all the parameter, precision, recall, F1 score, I'll explain everything. So first let me create one function and let me give the name confusion matrix. And let me pass the parameters. And over here, we'll give the figure and the axis. We'll plot just subplots. And let me give the size of the figure. And this is done with the help of the Svm library. And let me draw the heat map. and then we'll call the confusion matrix. Even we can just do the confusion matrix also. Let me just write it over here. We'll do one more thing. Wait. Um, okay, we have to pass this parameter LR for the predicate which we have done LR underscore Y underscore. This is the parameter. So now you can see this matrix. So this matrix would come, and this graph we were doing for showing you in the form of the graph. But I'll explain what actually this is, which it is showing you the value 25, 4, and 3, and the 29, the confusion matrix. This is the positive and the negative. So you have heard about the true positive. This is false negative, false positive, and the true negative. Let me explain the confusion matrix first. Let me open the Word file. All right. So for the confusion matrix, so over here we are taking the original value at the left hand side, original value. I'll increase the font. Yes. Original value, and at the top, this is for the side of it. This is for the left hand side, and it's easy to draw at the paint instead of this. And at the top, we are having predicted values. All right. And if you'll see, so we are having some positive and we are having some negative. Okay. So for that, we are having, if we are having both are positive, that is the original value we are having, and the predicted one, if both are say positive, that is the true positive value. So we are saying it for that. First is the TP, that is the true positive value. And the second column, it's for the negative, but the original we are saying it's the positive. And over there we are saying it's the negative. So it's a false, right? Because you are saying positive and it says negative, so that's a false. And it's a negative. So false, negative, Fn. And then we can just write over here the positive we are saying at this side, that is for the predicted one, we are saying for the predicted one it's the positive, but actually it's the negative. Then it's false, which we are saying, and it's a positive because we have predicted it's a positive. And then a negative, in this case we are saying it's a negative, and actually it's a negative. Original also say it's a negative, so that means it's true, and it's negative, that's why we are saying it's true negative. So that's the value of the confusion matrix which we are having. It will show you the true positive, false negative, false positive, true negative. I'll show you in paint also so that you can understand better. Let me go to file, new, and don't save. All right. So over here, let me go to home and let me take this pencil, and over here let me draw this. This is over here, and then this part. So this is for the predicted, and this is for the original. All right, and this is for positive, this is for negative. Same case for this, positive and negative. Positive, negative, you can say that 1 and the 0. You can take that also, 1 and 0. All right, so and it will show you that you are saying it's 1, and it's also saying in the original it's also 1, so that means you are saying true, and it's 1, that is positive. You are saying no, that is value 0, and actually it is 1, so that is you are saying wrong, that is false. So but you are saying 0, though negative. And you are saying 1, but in your original it's 0, so that is false again. And P, that is the positive one. And you are saying negative, and it's actually a negative, that is you are saying 0 and it's actually a 0, so that is true and negative true. So that is the confusion matrix. So for understanding precision and recall, you need to understand these things. All right. Okay. So now let's come to this part. So now we have seen that true positive is 25, false negative is 4, false positive is 3, and true negative is, so more it's likely to be positive, giving positive values. So because these diagonal false negative and false positive, it should be less. And that is coming less. So this model is working fine for us. All right. And there is another thing which I have shown, that is the this precision and the recall. So when we are calculating the precision, we are considering both positive as well as the negative samples that are classified. So over here, that's why we are saying its precision is like this. And when we are talking about the recall, so when we have to calculate, we only need the positive samples which we have seen. So negative, all the samples which we are having in the negative one, so we have just ignore it. All right. So when we are building any machine learning model, so the first thing that comes into our mind that how accurate or good fit our model is. And that's become the challenge, that because these precision and recall, these are the two most important concepts, and these are the performance metrics which we use for the classification, and it will give a more precise and the accurate result how our machine learning model is working, right? How more precise, and what is the balance between the, how the important to know the balance between the precision and recall. So we have understand the confusion matrix, and we have seen how many true labels we are having and how many false labels we are having. So on the basis of that, we have seen true positive, false negative, false positive, true negative. So this precision, we are having this formula, that is the ratio of correctly classified the only the positive samples to a total number of samples which we have classified incorrectly. So if we'll go over here, let me go to this part. Yes. So if we'll talk about precision, so it will tell us true positive PP and divided by whole true positive plus false positive. So like this. So it will tell you how we can correctly or incorrectly define. So this model we are defining from there. So precision of the machine learning model will be high when the numerator we can say, and this precision help us so that we can visualize the reliability of the machine learning model. So when we are classifying the model as positive, so it's saying 89, so that is a very good one. All right. And now for the, in the case of the recall, so we can just for the recall, we are just measuring the ability to detect positive samples only. Okay, so for this, we can just write recall true positive plus over here we are having true positive divided by true positive plus false negative. So this, to detect the positive samples, the higher value of the recall, the more positive samples were detected. So that's we have get it from here. And recall is independent of the number of the negative samples which we are having. And the model classify all the positive value sample as positive. Then at that case, our recall value is the 1. If they classify all the positive value as the 1. But it did not. That's why we are having recall as a 0.1 for this case, as you can see it over here, right? So that's how we have get it. And for the F1 score, there is another parameter, that is the F1 score. And there's another formula for that we are having. So when we are talking about the analysis of the binary classification, which we have done 0 and the 1. So this is measure of the test accuracy. So if you want to see what is the accuracy of that, what is the test accuracy, how we can perform, so that is we are using over here. And it just sums up the predictive performance of a model by just combining the matrices, precision and the recall. It just combines these two and it will give you the F1 score. That is the thing which they are doing it over here. So we are having this value. So if we are having a higher F score, so we can say the higher the F1 score, the better one. So with 0 being the worst possible and 1 is the best one for the F1 score. So it is most likely to 8. So that is a very good value which we are getting. Okay. So that's all the parameter which we have taken. So this, you can see this we have taken from here, that it is performing wisely good, this logistic regression. All right. So now, is there any doubt or should we move to the SVM? Okay, great, clear, that's great. It's your first time to understand these because there are so much concepts into it. So you will get it clearly when you will try. All right, so let's now start with the support vector machine, that is with the SVM. Let me share my screen. Okay, thank you, sir. Let's start with the support vector machine. And we'll apply on the same one, and you can practice on the that later one, the pneumonia, but we'll apply on the same because the data will take time to understand. Let me go to the slideshow. Yes, from current slide. So now see over here, we have to do the support vector machine. So first of all, the support vector machine, which we have to see this algorithm, how it works and why we are doing it, support vector machine, that we have to see. So this is we are in short form we are calling it as a SVM also, and the full form is the support vector machines. This is again a supervised learning method, and again this is used for the classification and for detecting the outliers. So all the tasks that are common in machine learning, we can do it in SVM. So basis of this, in this we have to do predict the driving routes or for our model that we need to do. So there are some specific type of SVM that we need to use for a particular machine learning problem. There is classification, there is regression also. So, but the main thing in mind which we have to keep is that the equation which we have to use so that it can give us the accurate answer and as quickly as possible which we require. This SVM is different from other classification algorithm. How? Because the way they choose the decision boundary and that maximize the distance from nearest data point of all the classes. So what is the decision boundary maximum? I'll explain it. So see the decision boundary that which we have seen, that is the 0.5 threshold value which we have taken in Logistic. But in this, they have created it dynamically, and that decision boundary we are going to take with the help of maximum margin classifier or the maximum margin hyperplane. So actually how this is work that we have to see, and this classifier we are saying that is much better as compared to logistic regression. or decision tree, because in this algorithm, in this we are having one kernel trick program, one kernel trick that is we are going to use so that we have to handle non-linear input spaces. So this SVM you can use in variety of application. For example, if you want to use face detection, if you want to perform intrusion detection, and if you want to even classify of emails, spam or them also you also use this. So again, we are going to use this scikit-learn library for this to understand. So generally, this support vector machine we are going to take as a classification approach. And for this, we are going to handle multiple continuous and categorical variable. First task which SVM has to do, they have to construct a hyperplane. Hyperplane in multi-dimensional space, it can be 2D, it can be 3D, so that we can just separate different classes. Now over here we are having binary classes, that is only two, right? But this works best when you are having a different classes also. So over there you have to just divide it into the different classes. So this SVM generates optimal hyperplane, that is the plane which we have to use. I'll just explain the plane what I'm talking about. So over here, you can see. Let me choose the size of the line also. Yeah, I guess it's fine. So see, we are having first two classes. Let's take class A. And then that is for the star. Class A we are having for the class A. And class B we are having for the triangle. Okay, so now you are having a mixture of two classes, and what you need to do, you need to draw, and these classes is a mixture like this. One is star, and there is one is like this, then star, then like this. So all the data is like, and you are having a two classes. So what you need to do, you need to divide a plane, you need to divide it into the category, so you can see. And this plane is divided that it can just set that the class A over here, elements, the nodes over here, and the class B. So it can just move, it can just find out a plane, an area where we can just divide the two classes in a good way. And after applying it, we can say after these classes, so when we found the hyperplane, this is the hyperplane. So all these stars class A lie over here. And all the triangles of class B will lie over here. Okay, so that's we need to construct into this, and this hyperplane, because it's not like that it will you will get it immediately, because there are many multiple of lines which you will get, and on to basis of that you have to find out which is the optimal, which is the best hyperplane you are going to use, and the best one is that which minimize the error, because we don't want the error, so that will minimize the error. We can say it's the best one, it's the optimal one. So the core idea of SVM is that we have to find this maximum marginal hyperplane that best divides our data set into two classes. So that is the thing which we need to do. And over here, the lines which you can see, the line which we are having, the most closest, as you can see, the most closest points which is closest to our hyperplane, we can say these are the support vectors, are the data points. These are the data points, and which is closest to the hyperplane, we are calling it as a support vectors also. So these points will define that we are separating the line better by calculating these margins. And these points are more relevant when we have to construct the classifier also. So this hyperplane which we are talking about, hyperplane, is just a decision plane which separates between a set of objects having different class memberships, right? So this is having a different class membership, and you have to divide a plane that is a decision planes which just separate between the two classes. And there is, when you will divide it, there is would be the gap between, right, over here. So margin, over here we can say it's a gap between the two lines on the closest class points. So there over here we can calculate the perpendicular distance from the line of the support vectors to the closest point. So this is and the closest point. So if the margin is larger between the classes, then we can say it's a good margin. And if a margin is lower, then we can say it's a bad margin. Okay. So that's how we do. And over here, so we are having so many classes onto which we have to perform. So first of all, how does this work? We'll see, because see, the main objective which we have to perform is to segregate the given data set and in the possible way. So we have to find the distance between the nearest point. So you can see this is the nearest point that we are calling it as a margin. And the objective is that we have to select the hyperplane, and hyperplane with having the maximum possible margin between the support vectors in the given data set. So this SVM will searches for the maximum marginal hyperplane. So first step, what it will do, it will generate the hyperplane. Let me draw it again. It will generate a hyperplane, and which will segregate the classes in the best way. So over here in this diagram, so for this, so for example, we are having this first class A. And let me draw this line. And over here, we are having this. And then we can also divide like this also over here. And then the lines. So the lines which we are generating as the three lines, you can see over here, these are having high classification error, right? And we have to find which is the in, because these are the planes which we have find out, and we have to tell which line is the better one, optimal, which is separating the classes, these two classes. First, see into this line. This is the first line. Over this, they are separating these classes and this, but there are some outliers which is just coming, so it is not a good one. And if you'll see this line also, but over here the class B outliers are lying, so this is also not the best, because there are some cases which when you are inputting not getting that. And the third case is this one, because your class A and class B is effectively divided. So we can say this line third is best one who is separating the two classes. So that we have to select the right hyperplane, which is having the maximum segregation from either of the nearest point. So you can see this. So the point, as you can see over here, this is the closest point over there, and this one. So these 2 points, which is closest to the this line which we have made, so it is called the support vectors. So we have to select the right hyperplane with maximum segregation from either the nearest data points which we have seen, and this. So over here we'll just draw the 2 lines with the just touching the support vectors, and this is the margin. These are the 2 margins. This is the margin which we are having. Yes, draw like this. All right. So what happened? This is the linear one. So when we are having, we can just separate it data linearly. But problem occurs when we can't divide the data linearly. So at that case, we have to use the kernel trick. So when the data is not linear, like when the data is like this. Now see this data. So tell me how we can divide it linearly. If we'll do like this, so see, it's not good. If we'll do like this, if we'll do like this, we can't. So this is a non-linear data. So some problems can't be solved using the linear hyperplane, right? As we have done it over here. So in this situation, we are going to use this SVM kernel trick so that we can transform the input into the higher dimensional space. So see over here, we are having the one dimension, and now we are going to change it into two dimension. If you're having two, then we are going to change it into three. So that is the data points which you are having plotted on the x-axis and the z-axis. What you need to do, z is squared, sum of both, then you get to calculate that. So that is the kernel trick which they have do, and there are basically different kernels for that which they are doing it. So first it will see it will convert it. So it between the variable x and the z-axis, and then you can see the data. The star will be the up at the top, and the triangle one will be at the bottom after applying the kernel one. So see this SVM kernel, this kernel transformation, we are just inputting the data, and into that form which we require, it will just change into the higher dimension. And for that we are using kernel trick. Kernel will take the low dimension input space and transform it into higher dimension space. So we can say it can convert non-separable problem into the separable one by just adding more dimension into it. So that's how we are doing it. In this we are having a different kernels. We are having linear kernel, we are having polynomial kernel. So a linear kernel, it will just use the normal dot product of the two observation, and it will just sum of that. Polynomial, what it will do, it will more generalized than the linear one, because it distinguish curved or the non-linear input space also, because it will take the degree of the polynomial, that what is the transformation which we require, and that we need to tell manually in the learning algorithm. So there are more of that. We'll see now the slides. So maximum marginal classifier, I'll explain multiple that we need to constrain optimization problem, and the kernels also, that if you need to go into the higher dimensions, we have to go with the kernels. And the complexity, it depends on the number of training examples we are giving it, not on the dimensionality. So it's just the data set which we are taking. So see, it is a linear separable as we are doing temperature. So we are taking temperature and humidity, the input, and we have to decide whether we can play tennis or not. So green is that you can play tennis, and red is not, you can't. And this is the best hyperplane which they have chosen. So this is a support linear, this is a linear support vector machine which is just dividing the linearly. So that's the value which we got it. And there are all hyperplanes which we have generated. As you can see over here, there are different hyperplanes by the vector and the constant with the equation. Just need to do the product, it's just a hyperplane. And we just need to find the best hyperplane that correctly identify, right? And defining the hyperplane, it's just that this is the equation which we are going to use and which will give you the positive result. So these two, H1 and H2, are the support vectors. So now, as you can see it over here, these are the support vectors over here, this, and you can see over here we are having these value also from where line are passing, and the mid value is the hyperplane, and the value, these lines which are passing from the green lines and the dot support vectors, these are the margins which we are having. So this arrow is the margin one, and D plus is the positive, because the terminology is used like this: the shortest distance to the closest positive point and the shortest distance to the closest negative point. So that's what we are using. And the margin of a separating hyperplane is D minus plus D plus. That is the margin. We have to add both the values. That is the margin which we are getting. And we want a classifier with a big margin as well. So the margin should be the maximum one. So in order to do that, we are just combining it, and there are no data points between H1 and H2. We should remember this thing. And these are the constraint optimization problem that we need to apply over this. and quadratic programming, which is done over here, that the fixed real number accuracy that can be called, and the maximization function. And this is the 2D also, the problems with the linear SVM. As you can see, if we are having this type of data, so how can we divide? Because the decision function can't be the linear over this, because the line which we can draw, it can't linearly separate it. So for this, there comes the kernel trick, which we have already studied. And these data points can be separable into the space. So that's the formula which we are using. And there are other kernels also. I told you polynomial kernel. This is the formula. Sum of it, we are just doing the cross product, and we are doing then sum of it, and this raised to the power p tunable parameter, which we can just give. And there is Gaussian kernel also. So it depends on which, that is, we are calling it a radial basis function. So it uses when we are having input space in infinite dimension space. So when we are having that, then only we can use this. So the parameter gamma is the parameter whose ranges lie between 0 to 1, and higher value of gamma will perfectly fit the training data set. And it goes overfitting also. So that's the thing which we are having. So that's the thing which we are having in the SVM, that we need to generate the hyperplane. I hope this is clear, so that we can just move to the practical part of the SVM. Yes, if data is not linearly separable, then we have to apply the kernels. That's what I said, that we have to apply the kernels, and we are having different types of kernels to separate it: linear kernel, polynomial kernel, and the radial one. So for that, we can use it to divide it. Okay, ma'am? All right, let's, because it's a shortage of time, so what we'll do, because I'll explain the SVM algorithm, I have explained, so we'll do the coding of the algorithm onto this only, the data set which we have taken onto the same data set, and I'll share the pneumonia data set and the code part with you, so that you can just see and apply how we can apply the SVM algorithm to over this. All right, is this fine with everyone?
Okay, ma'am. Thank you.
Okay. Okay, there is one question. Is there any procedure? So see, when you will draw the graph now, when you will draw the graph, so there is no such procedure that you have to set support vector value. The nearest value, the distance, what it will do, it will find the distance from the hyperplane, and according to that, it will check, okay, this is the support vector or this is the node. So it will find it according to the distance which we are having. And that is the statistics again. This is pre-built into the SVM algorithm. So we don't need to actually tell, okay, you have to take this support vector or you have to take this one. So, okay, so you're asking, is there any difference between? Okay. First, I'll answer the next question, that similarity between SVM and the spectral clustering. So first tell me where you can apply the spectral clustering. Yes. Because clustering is a different one, and over here we are doing the classification problem. Yes. So can we apply this? So the thing which you can say, the spectral clustering, or we can say this SVM, because SVM is used as because they are providing classification algorithm, which I am telling you, and you can use this SVM for clustering, that is for unsupervised, because there is a number of different ways you can just apply, because in that also we are giving the group values, and we are just finding that also. So we can just use this also. We can just say that SVM, this clustering algorithm, that if you want to introduce that, even you can just put the clustered data with this having a prior, with this not having any prior knowledge of input classes, and then you can just run this binary SVM classification algorithm onto a data set. With each vector you are having set randomly, because first what you will do, you have to set randomly labeled, and then you have to repeat the process, and when the initialization step is complete, then this SVM parameters you can use for the classification on each of these training instances that can be accessed. So over there you can use this in the clustering also for finding that out. So that's the value you can do. And this SVM based clustering methods also, they can improve the performance for different clustering algorithms that we can apply, and so that they can inherit the strengths of the supervised SVM counterparts also. So that we need to do, right? Okay. And okay. First we'll do the practical, then I'll explain this support vector value. All right, sir? Yeah, in the same way, let me just remove this line. And let me, for the SVM, we have to build, because we have not imported it. So first we need to import it, the libraries. So the first thing we'll do is import the SVM library, that is SVC. So from sklearn.svm, we have to import SVC. All right, and then just execute it. And then we'll just write our code. So SVM model, and we are calling SVC. And over here I'm passing the kernel, and I'm passing the RDF kernel. And let's take probability equal to 2. So the kernel, you have to decide which kernel you want to pass. You can apply linear also. So the SVM, first we'll do this. Done. And then fit extreme, the same one, and the Y train. And probability 2. Then again we can just find out the accuracy, that is the score for the training. And then for prediction, we'll just predict it. Done. And then let's print its value. So now again, it's in the form of this. And if you want to see the score of test also, so now you can see the accuracy and not accuracy but the testing model. And now we want to see the classification report and the confusion matrix. Now you can see the value of this, and over here logistic one is performing better. All right, and if you want to see the confusion matrix also, the same way we'll perform the confusion matrix. And over here we'll pass the test value, and then yes, this one. So over here we can see the values, and this would be our accuracy like 70%. So now as we can see it over here, it is not performing well onto this data set. First, the situation is that because we are having a less data set, that is, it works on the other thing. And because there are different parameters which we have to take for the SVM or the function which we are using, the kernel one, that is which we are using RGB, as we can see over here, the RBF function which we are using, it's not the best one which we are using, so we have to change it. So we are using just the radial basis function kernel. So first we'll apply for the linear, and for different algorithms we'll see which kernel is used over here. So this is the default kernel which is used with the SVM, and we can just say the gamma because they have two set, and they have indirectly because they have done the directly RBF, and the values which they are using it, they have done with the already which they have the values like that. So that is the linear kernel. Is we are saying it's never more accurate than the properly tuned RBF. But over here, because we are not getting the good results, we are not using this. So we can just apply for the linear one also and for the other one also. So that's why we can just see that. Okay, so this was all about the SVM and the logistic regression, and we have applied on the heart rate, and I'll share the content and the slides with ma'am so that you can see the code which we have done today and see the SVM algorithm and apply more onto the another data sets. So is there any doubt or which you want to ask? Then we can just wind up the session. Thank you, ma'am. Thank you so much. Okay, that's very great.
Okay, thank you, Shruti. Are you there, Shruti?
Yes, ma'am. Yes, ma'am.
So I hope all the queries has already been answered, because I was seeing that you were parallelly resolving their doubts. So as such, I'm not seeing any further, query in the chat window, but still we are online, and if you do have any query, the remote central coordinators can ask. Okay, thank you very much, Shruti, for such a nice session. And
Thank
we do have two more sessions of yours on day after tomorrow.
Yes.
So I hope that will add on to their knowledge, and the two algorithm that you have covered today, they will practice after receiving the contents. So thank you for joining us today, Shruti. Thank you very much.
Thank you very much. Thank you, everyone.
So see you all at 2:45 for the next session.